Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering and Hyderabad. So today we will discuss about definitions and terminology of thin cylinders and columns. So already we have discussed the theory part related to thin cylinders and also derived the equations and solved problems in thin cylinders and columns and struts. But you should focus on some important terms. So that is known as definitions and terminology of thin cylinders and columns. So today we will discuss some definitions and terminology of thin cylinders and columns. So before enter into the main topic, so you should know the outcome of this topic. So that at the end of the course, the student should be able to analyze the stresses developed and deformation of thin and thick cylinders due to internal pressure. So here, when a thin cylinder or thick cylinder is subjected to some pressure, internal pressure, so what type of stresses will be induced due to this internal pressure? You should know. So and then same as in columns also, whenever the column is subjected to load, so what will happen? Which type of stresses will be induced in the column? So all these things we will see. So this is the main outcome of this topic. Now the definition and terminology of thin cylinders. So actually this unit represents presents the analysis of thin and thick cylinder shells subjected to fluid pressure. So already we have covered in a theory part. Steam boilers, reservoirs, reactors, nuclear containers, tanks, working chambers of engines, etc. are the common example. So in this unit, the stresses and strains induced in the walls of the cylinder will be found out based on the geometry of the shell and the equilibrium of forces involved. Already we have learned, but we should focus in this. We will focus only the main definitions and some formulas only. So why? Because already we have derived in the theory part and also solved problems. But definitions wise we will see. So important formulas. So see here for the cylindrical portion, the cylinder having a cylindrical portion, the thin cylinder having cylindrical portion and hemispherical. So for the cylindrical portion, so W for circumferential stress. So how do you write the equation? The derivation part already covered. So here hoof stress sigma hc, the C here signifies the cylindrical portion. So PD by 2T. So T1, so that is the thickness of the shell. P is here internal pressure. And then D is diameter of the cylinder. And then T is thickness of the shell. So PD by 2T. So that is related to hoof stress or circumferential stress. The longitudinal stress PD by 40. So do you write? The longitudinal stress sigma L PD by 40. Same, the P is internal pressure and D is the diameter of the cylinder. The whoop or circumferential strain, how do you calculate? So stress already have seen, and then longitudinal stress also have written formula. But in this, the strain use this formula sigma epsilon 2. So that is circumferential strain PD by 41E into 2 minus mu. Here mu is the Poisson's ratio. So for the hemispherical ends, the cylindrical portion already we have seen. So for related to this hemispherical ends, what is the resisting force? Resisting force is equal to sigma h into pi into d into T2. So the resisting force is pressure multiplied with area. Is equal to sigma h, that is Wolf stress, and pi d into T2. This hemispherical ends area. See, the cylindrical cell. So this is cylindrical portion. Cylindrical portion, this is hemispherical ends. Hemispherical ends. Clear? This one, the thickness is T1 and here thickness is T2. So resting force is equal to whatever the stress multiply with Wolf stress multiply with area. So finally we will get for sphere portion, the Wolf stress is PD by 42. Similarly the Wolf strain. So write down this equation 1 by E into sigma h minus mu into sigma h. So finally we will get PD by 42E into 1 minus mu. So this is the Wolf strain relation. So thus equating the two strains in order to there shall be no distortion of the junction. So PD by 41E into 2 minus mu and PD by 42E into 1 minus mu, or T2 by T1 is equal to 1 minus mu by 2 minus mu. So for general, the steel works, the mu is 0.3. Therefore, the thickness ratios becomes the T2 by T1 is equal to 0.7 by 1.7. So here mu, substitute here T2 by T1 is equal to 1 minus 0.3 divided by 2 minus 0.3. So T2 by T1 is equal to 1 minus 0.7 by 1.7. So that you can write that T1 is equal to 2.4 times of T2. So the thickness of the cylinder walls must be approximately 2.4 times that of the hemispherical hands, for no distortion of the junction to occur. So you can write T1 by T2 is equal to 2.4. So summarize the derived results. Circumferential or Wolf stress PD by 2T, SH or sigma h, SL or sigma L, PD by 4T. Longitudinal or axial stress, circumferential or Wolf stress, not Wolf stress. Sigma h. Next, things the where D is the internal diameter and the wall thickness already you know. So longitudinal strain. How do you write the equation? 1 by E into sigma L minus mu into sigma h. Wolf strain 1 by E into sigma h minus mu into sigma L. So change of internal volume of cylinder under pressure PD by 4TE into 5 minus 4 V into volumetric strain, capital V. So from the thin cylinder spheres or circumferential Wolf stress PD by 2T. So you know, so that now the change in volume of thin cylindrical shell due to an internal pressure. So volumetric strain, change in volume of thin cylinder, delta V by V. The change in volume is equal to final volume minus original volume, that is delta V. So original volume and that is V is equal to area of cylindrical shell pi by 4 into D square into L. That is original volume. So now the final volume is final area of cross section multiplied with final length. So to write this equation for final volume, pi by 4 into D plus delta D whole square plus multiply with L plus delta L, neglecting smaller quantities. So that the final volume is equal to pi by 4 to D square L plus 2D dl into delta D plus delta L into D square. So change in volume delta V, the final equation, final volume calculated and original volume calculated here. So now substitute this change in volume, calculate delta V. 5 by 4, after simplification you will get, so D square L, 5 by 4 D square L plus 2D into L into DD, delta D plus delta L into D square minus 5 by 4 D square into L. So what is this minus 5 by 4 D square original volume? Final volume minus original volume, that is change in volume. First calculate change in volume and then calculate volumetric strain delta V by E. So volumetric strain, now substitute delta V 5 by 4 into 2D into L into delta D plus delta L into D square by 5 by 4 D square into L volume. So finally you will get 2 delta D by D plus delta L by L. So you can write this delta D change in diameter by original diameter or change in length by original length is called longitudinal strain and lateral strain. Longitudinal and lateral strain, you can write 2 sigma C plus sigma L. So circumferential strain, longitudinal strain. So finally, so delta V, you can write V multiply with strain, circumferential strain and longitudinal strain. So where the circumferential strain and longitudinal strain sigma y epsilon 1 L is substituted and finally we will got volumetric strain. So these are the important terms and definitions related to the thin cylinder. So main thing is here in the thin cylinders or thick cylinders, one is circumferential stress or whoop stress, second one is longitudinal stress or longitudinal strain, and the circumferential strain and volumetric strain. So these are the very important terminology. Next, coming to the columns and struts. So definition of column and strut. So a structural member subject to an axial compressive force is called a strut. As for definition, a strut may be horizontal, inclined or even vertical. So example, connecting rod, piston rod, etc. The structural member subjected to axial compressive force. So already have discussed in the columns and studs. So this is a structure member. So another member structure, just length L and length. So it may be vertical and also inclined. It also inclined and horizontal also. It is called as strut. So whenever this length is more than the strut, that structure is called as column. So but a vertical strut used in buildings or frames is called a column. So the long column, so the length when compared to the strut, the length is very high. So that's why these type of columns are used in buildings. So the failure between the roof and floor. So failures. What are the important failures of column and strut? It has been observed when a column or strut is subjected to some compressive force, then the compressive stress induced and compressive force, and P is the compressive force and A is the cross-sectional area of the column. If the force or load is gradually increased, the column will reach a stage that is subjected to the ultimate crushing stress. So beyond this stage, the column will fail by crushing. So that load is called as crushing load. So the important definition. Define crushing load. So beyond the stage means the column at which fails by crushing. That corresponding load is called a crushing load. The stress is called as a crushing stress. Next is buckling load. Buckling. A compression member does not fail entirely by crushing, so but also by bending. That is buckling. This happens in the case of long columns. So long columns does not fail due to the crushing whenever the column is structure is subjected to compressive load. So all the short columns fail due to their crushing. But if a long column is subjected to a compressive load, it is subjected to a compressive stress. So the compression member does not fail entirely by crushing, also by bending. That load is called as a buckling load. So if the load is gradually increased, the column will reach a stage that is starts buckling phenomenon. So define. You can write the question like this. Define buckling. So the load at which the column just buckles is called buckling load, crippling load or critical load. Define critical load or define crippling load. So for a long column, the value of buckling load will be less than the crushing load. Moreover, the value of buckling load is low for long columns, relatively high for short columns. This is also very important observation here. The value of buckling load is low for long columns, which is relatively high for short columns. So these are the terms important related to these columns and studs. Buckling, critical load, and then crippling load. Next, types of end conditions of columns and studs. In actual practice, there are a number of end conditions for columns, but we shall study Euler's column theory on the following 4 types of end conditions, which are important from the subject point of view. So one is both ends hinged. Second one is both ends fixed. And one end is fixed, other end is free. And one end is fixed and other end is free. So derivation part already we have covered in theory. So that no need to derive here. So we are discussing only the terminology and definitions. So now first one, both ends hinged. See what is the diagram? Both ends hinged. Here also hinged. And one end is fixed. So in this also it bends like this. And both ends fixed. It may be convexity and concavity. So other end is the one end is fixed, other end is hinged. One end is fixed, other end is hinged. And one end is fixed and other end is free. So one end is free, there is no, one end is free and one end is fixed. So there is no hinged or fixed. So these are the end type of end conditions of column. So according to these end conditions, you have to derive the Euler's formula. So Euler's formula is derived for buckling loads. So how do you calculate the buckling load for a columns? So whenever the column is both ends hinged, both ends fixed, and one end fixed and other end is hinged like this. So according to these conditions, you must derive the equation. So already we have derived in a theory part, and also we have solved problems. So these are the important terminology related to these the columns and the studs. So what we have discussed up to now. So the thin cylinders, that is important terminology. So once again see the important terminology for cylindrical portion. So first one is important terms and definitions here. Thin cylinder, and then whoof stress or circumferential stress, and then longitudinal stress, and then circumferential strain or whoof strain. In this, 2 conditions are there in thin cylinders. One is cylindrical portion, another one is for hemispherical ends. So hemispherical ends, the whoof stress have derived and the whoof strain also calculated. So here in definition terminology, no need to derive. So only thing you must write the equation only for the hemispherical ends. So how do you write the strain equation? And then how do you compare this T2 the thickness ratios from longitudinal thickness and the cylindrical shell thickness to hemispherical ends thickness, that is T2 by T1. So already you have written this T1 by T2 is equal to 2.4. So in examination, they may ask, so what is the ratios of thickness of a thin cylindrical shell? So ratio of thickness means 1 and a cylindrical and 2 hemispherical and thickness. So thickness of the cylinder walls must be approximately in examination, just you have to write T2 by T1 is equal to 2.4 only. So circumferential wove stress and axial stress have derived, and we have discussed about longitudinal strain, wove strain, and change in internal volume of cylinder under pressure, thin sphere circumferential or wove stress. See here, change in volume of a thin cylindrical shell due to an internal pressure. So in change in volume, delta V. So this is volumetric strain, delta V. Volumetric strain. What is volumetric strain? So you have to write the equation delta dV by V. But what is delta V? Again, you have to write the change in volume is equal to final volume and original volume. So what is original volume? You must write this equation. So final volume, final area of cross section, multiply with final length, and final volume already we derived. And change in volume also we have derived. Now calculate the volume. This is the final 10 volumetric strain. They may ask in examination, so define volumetric strain. Define volumetric strain. So first you have to give definition. Volumetric strain is equal to delta V by V, that is change in volume by original volume. So change in volume means final volume minus original volume, and then write this equation. So now finally the relation between this delta V by V and then strains, in the form of strains you must write the delta V is equal to the change in volume is equal to original volume multiplied with 2 strain, circumferential strain, and 2 multiplied circumferential strain plus longitudinal strain. So circumferential strain and longitudinal strain already we have written in equation. So next, column sum stress we have discussed about column and definition of stress. So in examination they will ask define column and define stress. Give examples. And what are the failures of column? So they may ask like this, what are the failures of a column or strut? So failures written here, so also discuss, and important terms in these columns and struts. One is crushing load, and second one is crushing stress. Third one is buckling load or critical load or crippling load, and stress also buckling stress, crippling load. These are the important terms related to this columns and studs. And also these four conditions also important. So the Euler's column theory based on these four conditions, both ends hinged and both ends fixed, and one end is fixed, another end is hinged, and one end is fixed, another end is free. And diagrams also shown the examples. So in the Euler's theory, Euler's scientist derived the theory based on some assumptions. So already we have covered in a theory part. So the assumptions are, one is always the column should be straight, there is no deviation, and always the column having uniform cross section, and material also homogeneous isotropic. So these are the some assumptions. So based on these assumptions, made this Euler's theory. So while solving problems, you must use this theory for buckling load and critical load calculations. Clear? So these are the main topics, and then references are Ramamurtam, S. Ramamurtam, and title of the book is 10th of Material, and publishers are Dhanpati Rai Publishing Company, and then R.K. Rajput, Strength of Material, S. and Co. Publishers, and R.K. Bansal, the other name, and the textbook is Strength of Materials, and R.S. Kurmi and Gupta. Title of the book is 10th of Material. So these are the references I have taken for this PPT for making of definition and terminology of columns and studs, and also for entire syllabus. These the four textbooks are very important references I have taken. So we have covered so far theory, and then problem solving, the critical problem solving questions, and then also we have discussed about some important questions on from question bank. So we have selected some questions from the question bank, and also we have discussed and derived problems and derived equations and problems. And also we have seen in the previous sessions discussed about some definitions and terminology from module 1 onwards. Simple stresses and strains, and then shear force and bending moment diagrams, pure bending, principal stresses and strains, columns and studs, and bending theory, the torsional loads and the springs. And in this section I have discussed about thin cylinders and Euler's formula and for columns and studs. So that so all topics covered in this strength of materials. So take any one textbook for further more clarification, for further problem solving. So do practice more problems and derive the equations, and see any missing problems and any missing definitions and terminology. So in these sessions, so you can refer from any textbook. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.